Hey guys, so today is lesson 4 on rates of change. Now, today's lesson and tomorrow's lesson, um, there are certain aspects of this that are going to feel familiar to you, but we're going to look at them through a different lens. We're going to look at them through a calculus lens because you're in calculus and that's the purpose, right? Um, I say that just as a small warning because inevitably sometimes kids will look at what we do and they'll say, well, why don't we just do it this way instead? Because I'll get the same answer. Well, that's great, but that's not looking at it from a calculus lens. One of the things this course is trying to teach us to do is perspective. It's to look at it from the perspective of calculus instead of the perspective of something else. Okay, so just keep that in mind as we go. So we want to look at rates of change today. And really, again, it's going to feel very familiar because we're really just going to be talking about slope. The slope of a tangent, which is what we dealt with in the last class, can be viewed as a rate of change. That statement should make perfect sense to you, right? Because any slope on a line is the rate of change of that line. Since the slope is the ratio of the change in y over the change in x, that is, slope equals delta y over delta x, we say that the slope is the rate of change of y with respect to x. In this investigation, we will look at other rates of change, starting with velocity. Okay, so suppose Sam drove to Edmonton, a distance of 300 kilometers, in 3 hours. We can use the following formula to determine Sam's average velocity. Average velocity would be the change in distance divided by the change in time, okay? You right away could say, well, he averages 100 kilometers an hour if he goes 300 kilometers in 3 hours, right? But when you say that, this is actually what you're doing. You're saying the average velocity is the total change in distance divided by the total change in time, okay? So we say delta S over delta T equals 300 over 3, which equals 100 kilometers an hour. If you're wondering about the S, S stands for spatium, the Latin word for space or for distance. Okay, that's where that S is coming from. Okay, so if you wanted to say it's all Greek to me, you can't. You have to say it's all Latin to me. But okay, Sam's average velocity is 100 kilometers an hour. Great. Does that mean Sam consistently was traveling 100 kilometers an hour? Absolutely not, right? There could be some moments in time where he was speeding and going 120 kilometers an hour. He could have seen a cop and gone down to 80 kilometers an hour, but on average, he did 100 kilometers an hour. So we were able to determine Sam's average velocity over time, over a time interval of 3 hours, but how do we determine his velocity at a given instant in time rather than over an interval in time? Okay, so we're looking at instantaneous velocity now, okay? All right, so the displacement of an object, new question, okay? The displacement of an object in meters is given by S, which is f of t equals 5t squared, where t is time in seconds, okay? So the displacement is f of t or S, and t is time in seconds. Complete the following table. Well, pause me and fill this in right quick. You're just plugging in 1, plugging in 2, plugging in 3 for t. You should have gotten 5, 20, 45, and 80. Okay. All right. Now, complete the following statement to determine the average velocity from t equals 1 to t equals 4. Well, if I think back to my first example with Sam going to Edmonton, if I want the average velocity, I take the total distance over the total time, right? Well, if I'm going from 1 to 4, right away, I can see the total distance is 75, right? Going from 5 to 80, okay? And the total time would be 3 if I'm going from T1 to T4, right? I'm just taking the slope. I'm going y2 minus y1 over x2 minus x1. That's really all I'm doing right there, right? Okay, so I said delta S over delta T, remember I want to phrase this from a calculus perspective, would be f of 4 minus f of 1, so that's y2 minus y1, divided by 4 over 1, which is x2 minus x1. Okay, so that's 80 minus 5, which is 75, and over 4 minus 1, which is 3. So I get 25 meters per second. Okay? All right, now you try going from 1 to 3 instead of 1 to 4. Pause me. Welcome back. So you're looking at, if I'm going from 1 to 3, my time value is 2, and my y value change would be 40. So I end up with 40 over 2, which is 20 meters per second. Okay. Okay, what if I wanted to go from 1 to 2? Some of you are catching on right away what I'm doing, aren't you? I'm approaching 1, right? I started at 4, and then I went to 3, then I went to 2. Anyway, 1 to 2. So my overall S change would be 15 over 1, which is 15 meters per second. Okay? Okay, with these last 3 questions, what are we doing? What are we approaching? Well, we're approaching 1. That should feel like a limit, right? Because that's what we've been doing for the last few days. Okay, so determine a simplified formula for the average velocity from t equals 1 to t equals 1 plus h. So my first x value is 1, my second x value is 1 plus h. Okay, so I'm still going to go y2 minus y1 over x2 minus x1. X2 minus x1 would leave me with h, if you can see that, right? Because that'd be 1 plus h minus 1. On the top, that'll be f of 1 plus h minus f of 1. Okay. Okay, well, I know f of 1 is 5, so I can actually change that. And then what I did for the other guy is I plugged 1 plus h in for t, right? So 1 plus h is my x value. So I just plugged it in. Sorry, my head was in the way there. I just won't go that way. I'll just plug it in for t right there. So if f of t is 5t squared, well, that's what I've done right here. I've gone 5t squared, but I've replaced t with 1 plus h. Okay. I could have done the same thing with 1, but I could have also just read it off the table here. F of 1 is 5. That's where that 5 came from. Yeah? Okay. Okay, cool. So I'm going to clean this up a bit. This will be 1 plus 2h plus h squared. Bring my 5 all through that. I just need to get my mouse back here, sorry. Okay, so then that's going to be 5 plus 10h plus 5h squared minus 5. So that ends up being, my 5's are gone. So 5h squared plus 10h all over h. I could factor out an h. Okay, and then that would leave me with 5h plus 10. 5h plus 10. So now this is a kind of generic velocity, average velocity function, 5h plus 10. Okay, so why don't we check and see if it actually works based on what we originally did. Okay, so go back to what you did. You looked at going from t of 1 to t of 4, and you ended up with 25. Okay, now think about this. This equation is set up going from t of 1 to t of 1 plus h. So essentially, h is the distance after 1, right? So if I was wanting to figure out that t of 1 to t of 4, h would actually be 3 there, because going from 1 to 4 is 3. Okay, so if I plug 3 in here, I get 5 times 3, which is 15 plus 10 is 25. That's exactly what I got in that first example. In the second example that we did, we went from t of 1 to t of 3, and we got 20. Well, my h value there would be 2. 5 times 2 is 10, plus 10 is 20. Okay, in the last example before we did this one, we went from t of 1 to t of 2, and so my h value there would be 1. And if I plug 1 in here, I get 15. So I'm getting the exact same things that I got using this generic equation instead of solving each one separately. Okay. Okay, so determine the instantaneous velocity at t equals 1. In order to determine the instantaneous velocity, now I'm looking at a limit for v of 1 where h approaches 0. Okay, so 1 because it's at t equals 1. Okay, and I just took that equation that I just figured out, which was the 5h plus 10, and I'm going to approach 0. Well, This one's a fairly easy one because I can do direct substitution. If I just plug 0 right in, I'll get 10. So the instantaneous velocity at t of 1 equals 10. Okay? Is there another way we could have done this? Well, yes, really, what we could have done is we could have calculated the limit from the beginning. We could have calculated the limit without obtaining this equation first, right? Really, that's what we did in the last lesson because the limit was just the slope formula. Think about where we got that 5h plus 10. I'm going to take you back for a second. Just let me get rid of this ink here. Where did we get that 5h plus 10? Let me just go back. Take a look at what we did here. Was not this first principles? Okay, I just didn't have a limit in front of it yet. But then in the second slide, I said, let's determine the instantaneous velocity, and I put a limit in front of my answer. Okay, so we could have done all of that right away just using first principles like we did yesterday. Okay, so let me go back to where we were and let's do it. So we'll go v of a equals the limit of f of x minus f of a over x minus a, where the limit as x approaches a. Okay, so now I'm using method 1 instead of method 2 just to show you again, it doesn't matter which one we use. Okay, so I want to look at the limit at 1. So I'm going to approach 1. T is going to approach 1. So I'm going f of t minus f of 1 all over t minus 1. Okay, so I'm using the point t comma f of t and 1 comma f of 1. Okay, all right, so f of t is 5t squared. And then f of 1 was 5. So I end up with 5t squared minus 5 all over t minus 1. Now I can't do direct substitution right now. The t minus 1 is in the way. So let's do some factoring. I can take out a 5 here, and that would leave me with t squared minus 1, which is the difference of squares, and that will factor into t plus 1, t minus 1. Okay, now my t minus 1s can divide out, and that gets rid of my problem. So I'm looking for the limit as t approaches 1 of 5 times t plus 1. So if I plug 1 into there, I get 1 plus 1 is 2, and 2 times 5 is 10. So the instantaneous velocity at t equals 1 is 10 meters per second. Okay, again, this is using method 1 of first principles. Okay, I'm going to go back for a second. This guy was essentially using method 2 of first principles, right? I just did it in 2 different steps. Okay, either way, we still get 10. Okay, cool. So if an object moves according to an equation s equals f of t, where s is the displacement or directed distance from the original position at time t, then s equals f of t is called the position function. Okay, the position function. Okay, the average velocity then from t equals a to t equals a plus h is given by average velocity is delta s over delta t, which would be y2 minus y1 over x2 minus x1. So y2 would be f of a plus h. Okay, just to make sure you're all on the same page with me here, I want to just paint this picture for you. My 2 points here are a comma f of a and a plus h comma f of a plus h, right? That's where I'm using, that's the 2 points I'm using for the slope formula. I apologize that my mouse writing is super messy. Just in case you can't see, I'm going to take myself away for a second, just in case I'm covering that. Okay. So that's where this formula is then coming from. It's y2 minus y1 over x2 minus x1. Okay, and so the velocity ends up being v equals f of a plus h minus f of a over h, and that's just because a minus a is nothing. Okay. Okay. The instantaneous velocity at time t equals a is denoted by v of a, and it's the limit of the average velocity as h approaches 0. Okay, so this hasn't changed. Let me just grab my ink again. This has not changed. That is still the average velocity that we just talked about in the last slide. The difference now is to get the instantaneous velocity, we take that average velocity as a limit where h approaches 0. Okay. So this means that the velocity at time t equals a is equal to the slope of the tangent to s equals f of t at t equals a. Okay, because that's what a limit is doing, right? The limit is telling me the slope of the tangent line that exists at that particular point. Okay, so the velocity is equal to the slope of the tangent line. They are the same thing, okay? All right. So let's try another one then. The displacement in meters of an object is given by s equals t squared plus 2t, where t is the time in seconds. Determine the average velocity from t equals 3 to t equals 5. Okay, so average velocity, I'm not looking for a limit yet. I'm just looking at the slope formula. I want to go from t equals 5, or sorry, t equals 3 to t equals 5. Okay, y2 minus y1, I can literally just plug in 5 to get my y2. I can plug in 3 to get my y1. So I'm going to go f of 5 minus f of 3 all over 5 minus 3. The average velocity is just the slope. Okay, so 35 minus 15, when I plug 5 in, I get 35. When I plug 3 in, I get 15. Okay, so that ends up being 20 over 2, which is 10. The average velocity is 10 meters per second. When you answer these, make sure you do have proper units on them as well. Okay? Okay. Determine the velocity at 3 seconds, okay? So now the velocity, because it doesn't say average velocity, that's now instantaneous velocity. So now we are looking for the limit, okay? So we will look at the limit as h approaches 0 of f of a plus h minus f of a all over h. So a is 3. So we're looking at f of 3 plus h minus f of 3. I already know what f of 3 is, right? And then what I'll have to do is 3 plus h gets plugged into here, right? All of this should feel familiar because it's very similar to what we did in the last lesson. Now we just have a context as to why we're doing it. Yesterday, I was teaching you, you just need to understand to do this. Now we're looking at a real world context where this is why we would do it, okay? Okay, so f of a plus h, remember that the formula is t squared plus 2t. So this right here is my t squared plus 2t. Okay, I'm just plugging in 3 plus h for t. And then I knew that f of a was 15 because I just plugged in 3 for my a value, or for the t value in this instance, right? Okay, so now I got to clean this up. 3 plus h squared would be 9 plus 6h plus h squared. Then we've got what? Plus 6 plus 2h minus 15. Okay, 9 plus 6 is 15 minus 15, so my numbers are gone. I've got h squared plus 8h all over h. So I can't do direct substitution right now, but I can factor out an h, and that'll get rid of my problem. So that will give me h plus 8. Then I can do my substitution, plug 0 in, and I get 8 meters per second. Okay, so the velocity at 3 seconds is 8 meters per second. Okay, so at that 3 second mark, this object is moving. Right at that point in time, this object is moving 8 meters per second. Okay. All right, a spherical balloon is being inflated. Determine the rate of change of the surface area with respect to the radius when the radius is 8 centimeters. And I am going to give you the surface area formula there, just in case you don't remember. Surface area is 4 pi r squared. Okay, so I'm looking for the rate of change of the surface area with respect to the radius when the radius is 8 centimeters. Okay, so I'm looking for a limit, and essentially I'm using the surface area formula as my the formula that I'm going to get my x1, y1 and my x2, y2 out of. Okay, so my a value is 8. So I'll have f of 8 here, which means I'm just plugging in 8 here. Okay, and then this will be f of 8 plus h. Again, don't let all the numbers screw you up. What this is this is the equation, but I've plugged in 8 plus h for my x value, or for my r value there. And this guy is my f of a, which I just plugged in 8. Okay, so 8 plus h all squared is 64 plus 16h plus h squared. Over here, I've got 64 times 4, which is 256. So I've got 4 pi times 64 plus 16h plus h squared minus 256 pi. Okay, I'm going to bring my 4 pi into all of those. So that's going to give me 256 pi plus 64 pi h plus 4 pi h squared minus 256 pi. My 256 pi's are gone. And I'm left with 4 pi h squared plus 64 pi h. I can factor the h out of that. When I factor the h out of that, I'm now able to do substitution, okay? So when I plug the 0 in here, this is gone and I'm left with 64 pi. So the surface area with respect to the radius, when the radius is 8 centimeters, would be the surface area is increasing at a rate of 64 pi centimeters squared per centimeters. Okay, so 64 pi centimeters squared per centimeter is the rate that this balloon is inflating at the moment. Okay, at that moment when the radius is 8. Remember, as soon as the radius is 8.1, that changes because we're talking about the instantaneous rate of change, right? But that's the rate of change at that moment. Okay, cool. All right, so that's it for today. Your homework is posted there, and then the next lesson tomorrow, we're going to take a look at infinite series. Okay, so that's something that we did in 20-1, but now we're going to look at it from a calculus perspective. It'll be quite fun, actually. Okay, so I'll see you there. Take care.